Okay, so here's the summary of the results. We have no limitation in terms of the size and shape of the individual part because we've got no autoclave. We're not restricted to the size of the pressure vessel. We have a continuous process, so we have a significant improvement in productivity. We have a variety of feedstock. We can use, as I say, waste materials. What the waste materials will do is they'll add MOE and MOR, okay, flexibility to our final panel. But also, interestingly enough, they don't significantly impact the flammability. We ran a fire test at Intertech in March of this year. We had an 8-inch polystyrene wall, and we all know how fire-resistant polystyrene is, with lightweight steel studs embedded into the polystyrene. And then we put 1.5 inches or 1.25 inches actually of this material on the face. We ran a 2-hour fire test, and we passed the ASTM E119, the fire test, including a hose stream with 1.25 inches of this material cast onto that wall. What was interesting about it is we ran 3 separate panels with seams between them, so because obviously if you're going to do a commercial installation, you're going to have seams, and the idea was to test and make sure that we didn't burn through at the seams. Ended up the seams were the best part because when they ran it, when they hit it with a hose stream, at the end of the day, the seams ended up being the strongest part. And then most notably is, we can get strengths from 80 psi to 9,150 psi, obviously depending on the density. The idea was to make the composite binder as strong as possible so that as we foamed it up and it got lighter and lighter, it retained as much of its original strength as possible. So typically what we're making now is we're making a product that goes from about 80 psi to about 700 or 800 psi with densities running from 26 to about 60 pounds per cubic foot. 60 pounds per cubic foot for those people that are involved in very nanoscale is about the same weight as water. So all of these materials will float. So here's an example and a comparison of autoclaved aerated concrete to the ATI composite. We have a better fire resistance than theirs. Theirs typically requires 6 to 8 inches to get a few hours of fire separation. Ours demonstrates a significant improvement over that. Our capitalization cost is in the order of 1.5 million, but that's for 350 cubic feet an hour. We have a company in Minneapolis making fire door cores, or interested in making fire door cores, and we think for less than $500,000 we could go down to that facility, build one of these smaller scalable machines that in fact would extrude this panel board for them to use in their fire door cores, again based on 2 hours, based on 1.5 inches or 1.25 inches of material. So as I said, we have an Intertech fire test based on 2 hours, and so we'd be interested in sharing that information with anybody in the audience or any of your associates. So here's where we're at the end of the day. We've done extensive work on this. In fact, I got an email on Friday saying that the patent application we filed in the U.S. Patent Office 4 years ago is going to be issued at the end of this week. I'm sorry? 1 minute left? Thank you. Okay, well, I'm going to move along here. So, there's a significant demand for new building materials here and in the Middle East. I talked about using salt water, desert sand and salt water. We've made this material based on desert sand and salt water, so it's got massive universal appeal. The rest of those attributes you can take a look at for yourselves because I'm running out of time. Hopefully we can read them all, or you can read them on the web when you get to look at this at the last minute. So participation options. What we're looking for is opportunities to work with local industry either to build these portable production facilities or joint venture opportunities where we'll take a particular resource or a fiber application and turn it into a finished product. And that wraps up my presentation, and I'd like to thank you for your time.